Aloha and welcome to our video on air masses. In this video we will describe an air mass, we'll explain the characteristic features of each type of air mass, and then we'll explain the influence of continental, polar, and maritime tropical air masses on the majority of North America. Okay, so in this picture we're going to look at air masses, and first thing we need to know is what an air mass is. And an air mass is just a large body of air that has the same basic properties within it. And when we talk about properties, we're going to talk about two of them primarily. We're going to talk about temperature and we're going to talk about humidity. Okay, so how much water is in there and then what temperature it's at. So when we name an air mass, we name it from where it's formed, and where it's formed is going to define its properties. So the first part of the name, we'll see that we can be maritime or continental. So we'll see maritime or continental in both the reds and the blues. And what that's going to tell me is its humidity. So if I have a maritime air mass, that means that it formed over water, and that means that it's going to be a wet air mass, meaning it's going to have some kind of moisture associated with it. If it's a continental air mass, then it formed over land, and we'll call that a dry air mass. So we can see the difference between a wet and a dry air mass. A wet air mass will have more moisture in it, it'll have a higher humidity level, versus a continental mass, which is a dry mass, which is going to have less water inside of it. Now we also talked a little bit about temperature, and temperature is going to be the second part of the name. Notice how we have polar and tropical. If I have polar air masses, that means it formed in the higher latitudes and it's going to be a cold air mass. If I have a tropical air mass, then it's going to form down in the tropics and it's going to be a warm or a hot air mass. And we can have a couple others. Sometimes you'll hear about an Arctic air mass, okay, and those are going to be super cold air masses. Or sometimes you'll hear of an equatorial air mass, which is going to be a warmer, like a hot air mass. But basically we'll name them. So if we look at a maritime polar, which is this one here, we know that it's going to be a wet, cold air mass. So as you can see, the name is going to give us an idea of what this air mass is like in reference to temperature and reference to humidity. Now our air masses are going to move. In the picture here you can kind of see a cold, dry air mass. So where did it form? It formed over the continent, so it'll be continental. Okay, and we know that because it's dry and it's cold, so it's going to be a continental polar air mass. So a cold, dry air mass, and that cold, dry air mass is going to move, and here it's moving southerly. For the most part, they'll move a little bit to the east as well. But this one's moving southerly, and what you'll notice is as it's moving, it's actually going to warm up a little bit as it travels, okay? And as it does so, it's going to dissipate. The edges of it are going to kind of blend into the other ones, or we'll see some interactions, and that's what we'll talk about in the next video. But these air masses do move. Normally, our polar air masses will move to the south. Our tropical air masses are going to move slightly upwards to the north. So we can see where we're setting ourselves up for some real interesting things happening when these air masses collide. Now, geographically, as these air masses move, we're going to see some changes. Generally, they're not very huge in nature, but we'll see some things going on. One of the ones they showed us were what we call lake effect snowstorms. And remember that the weather in our country is influenced by the westerlies, so it's going to move from the west to the east. So as these storms and these air masses move over the Great Lakes, they're going to pick up some of this moisture as they travel. As they do so, we expect to see a little bit more precipitation when they hit landfall, and that's what we have are these snow belts, which are caused by lake effect snowstorms. So because of this, we'll notice that the eastern shores of the Great Lakes all tend to have slightly more snow than the western shores because it's picking up the moisture as it's coming across. Now, we also talked about our rain shadows in mountains. As we have this air coming in and it gets lifted, it's going to cause this condensation, precipitation will happen, and then we'll have our drier air moving out this way. So locally, geographic features can influence these air masses, but we're going to be talking about some larger scale pictures here and global patterns coming up in the next couple videos. Okay, so that's it for this one. As always, good luck on your quiz, and we'll see you in the next video. Aloha and welcome to the video on fronts. In this video we will go over the formation of a front, we'll differentiate amongst warm fronts, cold fronts, stationary fronts, and occluded fronts. We'll describe the formation of a mid-latitude cyclone, and we'll describe how airflow in the atmosphere fuels cyclonic and anticyclonic circulation. So before we get started on types of fronts, we should probably discuss what a front is. A front is where we have two air masses and they're going to collide. In this case, we have the formation of a warm front, and a front is named for the type of air that is moving. So in a warm front, we're going to have a cold air mass. We'll just put that here. And it's going to be colliding with a warm air mass. And in fact, the warm air mass is going to be moving towards the cold air mass. And that's where we get this little interaction point right here. And this is where our front is. So if we take a look at the front, we can see over here that we have this warm air mass that's going to be moving in this direction into an area that is populated with this cold air here. So warm air, being less dense, is going to be forced up and over this cold air mass. And what we see is the formation of stratus clouds. So we're going to have some cirrus clouds that are going to be way out here in the far, and that's our clue that we have a warm front coming. We'll see some cirrostratus and altostratus clouds, and then right there at the front level is where we see this nimbostratus cloud formation here. And what you're going to get is some prolonged rains that are coming, like a long day's drizzle. It's not going to be a big storm, but you'll have that rain that's coming. Once you have this front pass, then you are in cold air. As the front moves over you, you'll notice that the air temperatures are going to be warmer afterwards. So a warm front, you can see it coming by looking at the clouds. You'll see a building up of the sky with clouds, first the cirrus, then the stratus, ultimately a nimbostratus, a gray sky with some drizzle, and then from there we'll get the warmer temperatures afterwards. Now in this slide we have a cold front, and remember we said it was named for the air mass that's moving. So here we have a region where we have some warm air that's settled in, and then we're going to have a cold front move through, or a cold air mass move into the area here. And it's right here is where we see this front formation. Now, a cold front's kind of like a bulldozer. So what we're going to have is we're going to have this cold, dense air here that's bulldozing its way into this warm air. So instead of having a nice gentle buildup of clouds, instead what we have is this cold front come through, and it's going to cause this warm air to really quickly rise up. And when we have that rising up, we're going to develop this cumulonimbus cloud, which is a thunderstorm. So we'll experience severe storms at a cold front. Now, if you were over here and you felt this, or you had this experience of this cold front coming through, what would happen is you would have nice warm days, and then all of a sudden you'd look and see these thunderstorms coming. One of the interesting things is if you look at the top of the thunderstorm, it kind of gets blown in the direction that it's going. So they call it an anvil cloud because it looks like an anvil, but it actually will point in the direction that it's going to be traveling. So you could see this coming. You'd experience some heavy, severe rains coming down. They're relatively short in duration, and then afterwards you'd be in this colder air. So you'll notice a definite cooling of the temperatures afterwards. And this is a cold front and how it forms and goes through. Now here we see the pictures of the formation for an occluded front. And an occluded front is kind of an interesting front if we look at it. What we have is we have a cold air mass that's kind of settled in here. And there's a warm air mass that's taking over here. It's kind of coming in this way. It's moving along relatively slow, but we have that warm front going. And then behind that, we have another cold air mass coming through, which is going to be traveling a little bit faster. So we have, in this picture, we notice we're going to have a warm front here, and then we'll have a cold front here. So this is how we set it up. And when we look in the picture, you can see we have our warm front here. Remember, a warm front means we have cold air. Warm air is on the move. And as it comes there, we get to see our cirrus clouds and our stratus build up. And finally, we get to our nimbostratus rains down here. So it's going to be kind of cool here. You'll experience a day-long rain, kind of nice and slow movement there. And then we have the warm air. Behind this warm air, we have this cold air that's moving also. And it's going to be moving a little bit faster than the warmer mass is going. So we have a cold front here. Now this cold front is going to be symbolized by our cumulonimbus storm clouds here, our thunderstorms, and our big storms on the end of this. And what we notice as we go down through the pictures is we're going to get to an occluded front here. And an occluded front is where we have a cold air mass that's going to join up with another cold air mass, and it's going to lift up a warm air mass in between them. So as we look at it, initially we're going to have a cold air mass here, a warm air mass here, and then we'll have another cold air mass coming here. And this cold air mass in the back is going to be traveling the fastest. So in the next picture, in picture number 2 here, what we're seeing is we still have that first cold air mass, but now we have this second cold air mass is joined up with it, and our warm air is now going to be lifted up to here. And we can see some storm and rains going on that way as well. So this is how we have an occluded front, and we can see that one right here. Okay, and what we're talking about is basically we have cold air, warm front coming through, and there's a cold front that's traveling behind it a little bit faster, and it'll eventually scoot that warm air up and out. Okay, in this picture there's a bunch of different things. It's a little bit of a summary for us. We'll start off with our cold front. Remember, we have warm air on this side, cold air on this side. The cold air is moving in this direction, and we're going to see these thunderstorms, these cumulonimbus clouds forming. On a weather map, you'll see a cold front, and it's going to be represented here by our blue triangles. Now, blue's going to be cold, triangles kind of sharp, so this is where we have severe weather for the most part, and the arrows are going to point in the direction that that front is moving. So if you look on a weather map and you see these blue arrows moving, pointing in a direction, that's where the cold front is going to be moving towards. Now in this picture we have a warm front, so we have cold air that's in, and we have warm air on the move. And remember, as warm air goes, it's going to kind of slide up here, and we're going to get our cirrus clouds, our stratus clouds, and finally our nimbostratus, light drizzly rain clouds here. And a warm front is going to be a lot gentler. So what we'll notice is our symbol for a warm front is going to be a curved half moons like this, and then they're going to point in the direction that the front is going to travel. So our cold front's going to head up the page, our warm front would also head up the page, as this example is. Then we have our occluded front. Remember, the occluded front is we had a cold air mass, there was a warm front coming in, and then we had another cold air mass that was moving closer, and it kind of comes together and they push that warm air up and out of the way. So an occluded front's going to move. It'll look like this. We generally will use both symbols, and sometimes when you look at a weather map, the occluded front will be in purple. They'll kind of purple it out, and we can see that in a later slide. And then there's this last front that we didn't spend a lot of time talking with, and this is quite simply a stationary front. And a stationary front is exactly like it seems. We have a warm air mass moving one way, we have a cold air mass moving the other way. They're kind of bumping into each other, moving back and forth a little bit. There's not a lot of motion, so that's why we call it a stationary front. And for the most part, it's going to be warm and cold. It's really kind of neat if you find one. You can drive from the warm side to the cold side, and you can actually feel the temperature change. So stationary fronts don't really move much. We don't see an awful lot of weather with them. One of the things, though, I do want you to know is if you notice here in the warm front we saw weather, in the cold front we saw weather, the occluded front we saw weather, and even the stationary we see a little bit. Most of the times when we see weather, it's going to be in these front situations where these air masses are colliding with each other. Okay, so this series of pictures is going to show us how we develop these low pressure cyclone systems. So what we'll notice is we have situation number 1 over here, and that's going to be situation 1 here, and we're going to kind of move this way as we go down on our track of time this way. So initially we're going to see this stationary front, which we see right here, and it's going to be here. Remember, that's where we have a cold front and a warm front. They're kind of moving side to side. They're not really moving back and forth an awful lot. Now, over time, we're going to see the warm air is going to start moving a little bit. Remember, we have the Coriolis effect. It's going to bend a little bit. We're going to start seeing a little indentation here from the warm air. The cold air is pushing up. It's going to start to bend this line a little bit. And what we'll see is we see that over here in situation number 2, where we're seeing that little bend. Now, as time goes, this bend gets a little more pronounced. And now what we have is we have this warm air moving, which is now going to turn into a warm front. And we see that by the red air half moons facing this way, and it's going to be moving in this direction. But we also see a cold front forming over here, approaching in on the warm, and that one's going to go in the direction that we see the arrows form. So if we look at our picture here, what we see now is we see a warm front moving this way and a cold front behind it moving this way. And that's going to give us this kind of circular nature that we call our cyclonic systems. As we go a little bit further, we have this cold air catching up and we get this occluded front here, and you can see that it's purple in this example, with our still warm front here and our cool front over here. So we can see how the storm is going to continue to build and it's going to continue to go. And then ultimately we get into this huge system over here. We still have our low. Notice that the winds are going to circle around this way. We have this rotational form here. We still have our severe weather coming here on the cold front. We have our warm front here. Everything's kind of breaking up. And then ultimately it blows itself out. It'll kind of mix up, and then we have the dissipation of the storm system here. So this is how we form these mid-latitude cyclonic lows. Is you'll see how we start off, we'll have this low pressure going. It'll slowly start off with a stationary front, and then we'll start to form these other fronts, and you can see how it's going to spin around a little bit. Now, when we have cyclones and anticyclones, or high and low pressure systems, you can see how this is going to move our fronts around. Okay, most low areas are going to pull the air inside of them. So it creates this little vacuumy kind of system here. That wind's going to move upwards in a cyclonic fashion, and then it's going to kind of dissipate its way out. So this is how we have our low pressure systems here. Our high pressures are this opposite. We're going to be taking some air in. It's going to kind of cyclonic way down, and then it's going to dissipate when it gets down onto the ground. So we always are going to have our wind going from our highs to our low pressure systems, and that's what's going to drive these fronts going along. So when we have these highs and lows, in between them is where we're going to see this weather formation that we're used to. So we can see our cold fronts and our warm fronts in between the two, because that's where the wind's going to be blowing these air masses and causing them to interact with each other. Okay, so that's it for our video. As always, good luck on your quiz, and we'll see you in the next video. Aloha and welcome to our video on severe storms. In this video, we'll explain the formation of a thunderstorm, we'll describe the conditions needed for a tornado to form, and then we'll identify the conditions that must exist for a hurricane to form as well. Okay, let's talk about thunderstorm development. Now, thunderstorms are characterized by a lot of vertical development, which means we have a lot of change in altitude with the storms. So there's a lot of uplift, and that uplift is what's going to cause an awful lot of the products of a thunderstorm per se. So we're going to start off here in our cumulus stage. And we have just cumulus clouds. There's going to be warm air rising. You're going to see this uplift coming up and things of that nature. And then we get from here, it's going to continue to build. So this storm is going to continue to build upwards. You're going to see the clouds bubbling up and things of that nature. And we get to our mature stage of a thunderstorm. Now, in the mature stage, we have all of these water molecules moving up and down. They're going to generate that static electricity, and that static electricity is released in lightning. So that's how we get our lightning for these storms. This rain that's coming down, this precipitation that's falling, can get caught in the updraft, and it can continue to build and build and build, and this is how we develop hail. So now we can see how we're getting lightning and hail from these thunderstorms, from this uplifting of all of this material. And that's what's going to cause these storms to develop so strongly. We'll look at tornadoes a little bit later, but they're also a product of this strong uplifting. That's what causes these storms. Now, when the storm runs out of energy, we get to the dissipating stage, and you'll see the rain start to slow down. Now, when it dissipates, there's a couple different ways this can happen. You can have a nice gentle dissipation like we see here, where the rains just kind of taper off, the clouds are just kind of, you see this down coming, all of this stuff's going to be collapsing down. There's no longer the uplift, so all of the precipitation and stuff's going to just keep falling, no more hail. It just kind of pitters out a little bit. But you can also have this where it's rapid. So you can have all of this uplifted material just give up the ghost, so to speak, and it'll all just drop down, whoosh, at one point in time. And this is what causes a downdraft. And we can have downdrafts where the winds produced by this downdraft of material are going to be in excess of 200 miles an hour. And we can see this because you'll have a point of impact, and then everything like trees and stuff will all blow down away from this point of impact. So you can see that it's all straight line winds that have caused this damage. And that happens when you have these thunderstorms. They give up their energy and it just kind of goes down. The bottom falls out of it, so to speak. And you can actually see that occur. So thunderstorms are pretty cool. When you see them, the safety is to get inside, get out of their way. Don't be on electrical devices in case it strikes the house or something of that nature. Watch out for the lightning, watch out for the hail, because they are fairly dangerous. But remember, it's from a cold front, so it's going to be kind of rapid in their progression. So the storm will come and then it'll be gone in a short period of time. So continuing along with our thunderstorms here, we can see we have our thunderstorm over in this area here. We have this updraft going on over here. But you can see that we have weaker winds blowing in one direction along the surface, and they could be weaker because of the friction of the ground. And then we're going to have these stronger winds aloft. And because of that, we get this kind of circular, this horizontally circular axis of spinning going on here. And then when that reaches that updraft that we see here, we can see how it's going to take this circular nature and it'll actually turn it. You can see it lifting it up here into where the clouds are. And then we get into this mesocyclone, which we'll see here, where we have this air is inflowing in with this updraft and we're getting this circular nature here. And as that happens, it's going to cause the entire cloud to rotate. So you know it's a bad scenario when you see these thunderstorms. This can be like a mile wide, and this whole thing is going to be turning like this. You're going to see this whole thunderstorm start spinning, okay? And when that happens, the net result of that is we'll see from the bottom is where we form our tornado, and that's where it'll work out that way. Inside the tornado, you're going to see a bunch of smaller cyclones spinning, so they're really devastating. We'll talk about that a little bit more in the next slide, but this is how we form a tornado. So when we're talking about tornadoes, we measure them on an intensity scale named after a scientist by the name of Fujita. So you'll hear about this Fujita tornado intensity scale, or the Fujita scale. Now, their intensity, and this is a little bit different because we're looking at wind speed estimates and things of that nature. So we go from an F0, where we're going to have light damage, broken branches might happen, small trees might get pushed over, signboards, all the way up to an F5 tornado, where the wind speeds can be in excess of 419 kilometers per hour. And this is where we see houses being lifted off their foundations, automobiles flying through the air in excess of 100 meters. We can see the bark ripped off of trees. So these are our very strong and damaging storms. So we use the Fujita scale to kind of rate these tornadoes and see how bad they are. So in this picture here, we're looking at a cross-section of a hurricane, and a couple different things we want to know. We're going to know that we have the wall of the hurricane, which is this outer edge here, and then we have an eye wall inside. And inside the eye of the hurricane, we actually have a moment where we have clear skies, because it's going to be open to the sky above here, and it's going to be relatively calm. However, just inside of the eye wall is where we're going to experience the strongest winds of the hurricane. So what we notice is we have this surface convergence of the wind that's going to be blowing around this way. And as it's blowing through, it's going to spiral its way up through the hurricane here, up to the top. And then from there, we'll get some outflow at the top, but we also will notice that we get some downdraft coming down inside as well. And that's what kind of clears it out, is that downdraft in the middle of the eye of a storm. Now, as the direction of this hurricane is traveling, what it's going to do is, because it's so strong, it's going to be pushing up this water ahead of it. And this is what we call our storm surge. And this can be just as damaging as the hurricane itself, because we can add like 15 feet of water in front of this hurricane as it hits shore. So let's take a look at how we rate hurricanes in the next slide. And just like the tornadoes had a rating scale, so do our hurricanes. And we use the Saffir-Simpson hurricane scale. So we can have a category 1 to a category 5 hurricane, and they're determined by their wind speeds. So at about 119 kilometers per hour, about 75 miles per hour is for our hurricane. And then we'll notice that we can get in excess of 250 kilometers per hour. Now, as I mentioned in the slide previously, we see this storm surge coming on here. With a category 1, we get about 1.2 to 1.5 meters. So we're talking about 3, 4, 4.5 feet of water increase as it's pushing onto shore, all the way up to excess of 15 feet here, where we can see with a category 5 hurricane. And that causes a lot of damage. That's going to cause that coastal flooding and things of that nature. The winds are going to be severe. It's going to be complete roof failure. You get a bunch of water coming down. So it's just a big storm that's going to be kind of concentrated into this area, and it's going to push ashore, and that's where we have our issues. Okay, so as always, they'll explain these things a little more detail in the lessons. Good luck on your quiz, and we'll see you in the next video.